In this video, I'm going to talk about the different techniques of differentiation, right? So we'll talk about chain rule, product rule, and then quotient rule. And then after that, I'm going to talk about how we can differentiate trigo functions, logarithm functions, and exponential functions. Okay, so let's start with chain rule. Okay, so let's look at the first example. Okay, so normally when you're asked to differentiate something like that, well, we may not want to use chain rule. We could have just expand it, right? So we can expand it and it'll become 4x squared plus 4x plus 1. And then dy dx would be 8x plus 4, right? So that's quite simple. Okay, but let's look at example 2, right? So if I raise the power to a 10 instead, this is quite big, right? So normally it wouldn't make sense to try to expand, right? Even if you use binomial theorem, it will be quite a hassle. So this is where chain rule is useful. Okay, so how does chain rule work? Okay, so first of all, we can let u be 2x plus 1. Okay, so y becomes u to the power of 10. Okay, and we can find du dx. Okay, so du dx is 2. And dy du would be 10 times u to the power of 9, right? So dy dx is equals to dy du times du dx, which gives us 10 u to the power of 9 times du dx is 2. So that is 20 u to the power of 9. So notice that u is equals to 2x plus 1. So we shouldn't just leave it in terms of u, right? We should bring back the x. So bring back 2x plus 1 to the power of 9, right? So that completes the differentiation. Okay, so that's basically how chain rule works, right? But the shortcut is actually pretty simple, right? So we don't have to go through all these steps to get the answer. Okay, so a simple way to do it is to, okay, so we have the dy dx, and then we just bring down the power 10, right? So just bring down the power 10, and whatever we have, right? So the power would minus 1, okay? And then after that, multiply by the derivative of what is inside here, right? So when we differentiate 2x plus 1 with respect to x, we will get 2. Okay, so you can see that this is actually a much faster procedure. Okay, and then yes, we get the same answer. Okay, so this is how we use chain rule. Okay, so let's look at the next example. Okay, so this is quite similar, right? Power 10, a rather big power. So I'll apply the same technique, right? So when we differentiate this, I'll bring down the power, keep what is the same for the inside, and then the power would subtract by 1. So that makes it 9 now. And then after that, multiply by the derivative of what is inside, right? So when you differentiate this, you should get 2x plus 2. Okay, so you can actually take out the 2, and this becomes 20 of x plus 2 times x squared plus 2x to the power of 9. Okay, and then that's it. Okay, let's look at example 4. So this is the square root, but the square root is also the same as power half, right? So I will apply the same rule, right? So it doesn't really matter whether this is power half, power 10, power 2, or power 1 even. Okay, so the same applies. So I'll bring down the half. Okay, I'll keep what is inside. The power would subtract by 1. So half minus 1 is negative half. Okay, and then we multiply by the derivative of what is inside, which is just a 2. Okay, so 2 times half is just 1, right? And this is 2x plus 1 to the power of negative half, which is 1 over square root of 2x plus 1. Okay, and then we are done there. Okay, so let's look at the next one. Example 5. So similarly, I can also write this as 2x plus 1 to the power of negative half. Right, so if you differentiate, you can bring down the negative half, and this is 2x plus 1. Power negative half minus 1, that will be negative 3 over 2. Right, and then multiply by the derivative of this, right, which is 2. So our final answer would be negative 1 over 2x plus 1 to the power of 3 over 2. And you can write it as 1.5. Okay, so let's look at example 6. So pretty much the same thing. So this is 2x plus 1 squared and then cube root. So that is as good as power 2/3. Right, so you can differentiate. This will be 2/3, and this will be 2x plus 1 to the power of 2/3 minus 1. That's minus 1/3, right? So multiplied by the derivative of inside, and that's 2. So our final answer will be 4/3. So I'll bring this down, and this is a cube root of 2x plus 1. Okay, so that sums up chain rule with some simple examples. Okay, so let's look at product rule now. Normally we use product rule when we're asked to differentiate a product of two different functions, right? So let's call them u and v. Okay, so this is the product rule, dy dx, right? So dy dx is equals to u times dv plus v times du. Okay, so if you look at this case, well, normally you could also expand it and just differentiate, right? So that would be pretty simple. But let's say if you want to use product rule, I can let this be u and let this be v. Okay, so du would be 2, right? Du dx is 2, and dv dx is just 1. So dy dx is equals to u, which is 2x plus 1, times dv dx, which is 1, plus v, which is x minus 3, times du dx, which is 2. Okay, and I can simplify the answer. This is 2x plus 1 plus 2x minus 6. That will give us 4x minus 5. Okay, so let's look at example 8. So for example 8, we have to apply chain rule right here. Okay, so I'm going to let this be u and I'm going to let this be v. Okay, so u is 2x plus 1 to the power of 20. And v is just x minus 3. So dv dx is 1. And du dx is 20 times 2x plus 1 to the power of 19 multiplied by the derivative of inside, which is a 2. So that will make it 40 times 2x plus 1 to the power of 19. Okay, and dy dx would be u times dv dx, which is this. Okay, this is u, dv dx is just 1, plus v times du dx, right? Du dx is 40 2x plus 1 to the power of 19. Okay, so for this case, we can actually factorize out the 2x plus 1 to the power of 19. Okay, so that would leave us with a 2x plus 1 here, plus a 40 times x minus 3. Okay, so we can actually simplify this. All right, so this is 2x plus 48. This is 42x. And this is 1 minus 120. All right, so that's minus 119. Okay, so that completes the differentiation. Okay, so let's look at example 9. So the same thing, we're going to let this be u and we're going to let this be v. All right, so u is 2x plus 1 to the power of half, and v is 3x squared. All right, so dv dx would be 6x, and du dx is half, 2x plus 1 to the power of negative half. Okay, and then multiplied by the derivative of inside, which is a 2 again. So this is just 1 over square root of 2x plus 1. Okay, so dy dx would be equals to u times dv dx, which is 6x, plus v times du dx. Okay, so du dx is 1 over square root of 2x plus 1. So I can just write it like that. Okay, so if I want to simplify this, I can actually multiply the top and bottom with something, right? Okay, so in this case, I would change it to the same denominator, right? So this is 2x plus 1 to the power of half. So I can multiply it by square root of 2x plus 1. Okay, so this is how it will work, right? So if I multiply it to square root of 2x plus 1, this will just be 2x plus 1 times 6x over square root of 2x plus 1 plus 3x squared divided by square root of 2x plus 1. Okay, so now they have the same denominator, we can combine it, right? So this is 12x squared plus 6x plus 3x squared over square root of 2x plus 1. Okay, so that will give us 15x squared plus 6x divided by square root of 2x plus 1. Okay, and that completes the differentiation. Okay, so let's look at quotient rule now. Right, so we use quotient rule when we are going to differentiate a quotient, right? So a fraction like this. Okay, but so for quotient rule, strictly we're going to let the numerator be u and the denominator be v, right? As I've written here. Okay, so an example, question 10, right? Example 10. So normally for such a question, I wouldn't use quotient rule, right? Because I can actually simplify it. I can actually write it like this. Okay, so I can split it up, and this is x squared divided by x to the power of half. That's x to the power of 1.5. And this is just x to the power of negative 0.5. Okay, so I can differentiate using chain rule, right? So there's a chain rule here. Bring down the power, 1.5x to the power of 0.5. Okay, multiplied by the derivative of x, which is just 1, right? So I'm not going to write that. And this is negative 0.5x to the power of negative 1.5, again, times 1. Okay, so this is our dy dx, right? So I could leave it like that, or I could, write it like this. So it doesn't really matter, actually. Okay, so if you want, you can elaborate 1 power 1.5, right? That's actually the same as power 3/2, right? Which is cube root of x squared. Okay, but that's not really necessary. Okay. Okay, but let's look at example 11, where we would probably want to use quotient rule, right? Okay, so how do we use it, right? We're going to let this be u and this be v. Okay, so let's write it out first, right? So u is x squared plus 1 to the power of 10. And v is x to the power of half. So du dx would be 10 times x squared plus 1 to the power of 9 multiplied by the derivative of inside is 2x. And dv dx is half x to the power of negative half. Right, so that's 1 over 2 square root x. Okay, and dy dx is equals to v times du dx. So v is this. du dx is 20. Okay, 20x times x squared plus 1 to the power of 9. Okay, so that's v times du dx minus u times dv dx. Okay, so this is u, and dv dx is 2 over square root x. Okay, and the whole thing is divided by v squared, right? So v squared is just x. Okay, so how do we simplify this fraction? Okay, we can simplify it by multiplying 2 root x to the numerator and 2 root x to the denominator. Okay, so when we do that, okay, so the numerator is going to be, this will be 2 times 20, that's 40x. Okay, so 40x, and root x times root x is x, right? So x times 40x is x squared. Okay, so this will be x squared plus 1 to the power of 9. 2 root x will cancel out this 2 root x, so this is minus x squared plus 1 to the power of 10. Okay, divided by, okay, 2 root x times x is 2x root x. Okay, so you want to combine it, you can write it as x to the power of 1.5. Okay, so we can simplify further, okay, by factorizing out x squared plus 1 to the power of 9. Okay, so this will be 40x squared minus x squared minus 1 over 2x root x. Okay, so that should be good enough, right? You can simplify 40x squared minus x squared to 39x squared. Okay, so let's look at the derivative of trigo, right? So how do we differentiate trigo, right? So let's start with the basic one first. Okay, so when we differentiate sine x, you should get cosine x, right? Okay, so just remember these results first. Okay, so to derive them is not so easy, right? So we are doing some basic differentiation here. Okay, so dy dx would be negative sine x. Okay, and dy dx for tangent x is actually secant square x. Okay, but I want to show you how we can use quotient rule to derive that. Okay, so first of all, you need to know that tangent x is equals to sine x over cosine x. Okay, so I'm going to let this be u and this be v. Right, so dy dx would be v times du dx, right? Du dx, that means differentiate sine x, so that should give you cosine x. Okay, minus u times dv dx, right? So differentiate cosine is negative sine, right? So this is negative sine x over v square. So over cosine square. So if you notice, the numerator is actually cosine square plus sine square, right? And the trigo identity tells us that this is 1. So this is actually equals to 1 over cosine square x, which is equals to secant square x. Okay, so that's how we arrive at secant square x. Okay, now let's look at example 15. Okay, so y equals to secant x. Secant x is actually 1 over cosine x. Okay, well, I could have used quotient rule, but I think I wouldn't. I would just use chain rule, right? Because that's the same as cosine x to the power of negative 1. So if I were to differentiate, I would get negative 1 times cosine x to the power of negative 2, multiplied by the derivative of the inside, which is cosine x, right? So differentiate cosine x, you should get negative sine x. Okay, and if you simplify that, we're going to get sine x over cosine square x, which is the same as sine x over cosine x times 1 over cosine x, right? And that will be sine x over cosine x is tangent x. And 1 over cosine is secant. Okay, so when you differentiate secant x, you will get tangent x times secant x. Okay, so let's try it for cotangent x as well. Right, cotangent is 1 over tangent. Okay, so again, I'm going to use chain rule. Okay, so 1 over tangent is tangent x to the power of negative 1. And dy dx would be negative of tangent x to the power of negative 2, multiplied by the derivative of tangent x, which is secant square x. Okay, so we're going to get secant square x, okay, negative secant square x over tangent square x. Okay, so tangent x to the power of negative 2 is 1 over tangent x to the power of 2, right, which is tangent square x. Okay, so if you want, you can simplify this further. Okay, but I'll just leave it like that. Okay, let's look at example 17. Okay, so again, I can use chain rule here. Okay, so dy dx, I'll bring down the 2. Right? This is sine x to the power of 1, multiplied by the derivative of sine x, which is cosine x. Okay, so 2 sine x times cosine x is a double angle, right? You can actually write it as sine 2x. Okay, and as for question 18, right, we can use product rule here, right? We can let this be u and this is v. So dy dx is u times dv dx plus v times du dx, right? But du dx is just 1. So the answer is x cosine x plus sine x. Okay, and as for question 19, we can use quotient rule, right? We can let this be u and this be v. Okay, so dy dx would be v times du dx, which is cosine x, minus u times dv dx, which is just 1. over v squared. Okay, so our final answer would be x cosine x minus sine x over x squared. Okay, now let's look at how we can differentiate logarithm. Okay, so the standard one is quite simple, right? Y equals to ln x, dy dx is just 1 over x, right? So in general, if you have y equals to ln of fx, the derivative of that would be f prime x over fx. That means we differentiate what is fx and then we divide by fx, right? So ln x, right? So fx is x here. So if you differentiate x, you get 1, right? So it's 1 over x, right? So similarly for this, the fx is x squared. So if you differentiate x squared, you get 2x, okay, over x squared. Okay, so you can simplify that to 2 over x. Okay, so for example 22, we can use chain rule. Okay, so dy dx, the power, I'll bring it down. So this is ln x to the power of 1. Okay, multiplied by the derivative of this, right? So differentiate ln x is 1 over x. So our final answer is 2 over x times ln x. Okay, now let's look at an example where the base of the logarithm is not e. Okay, so this is a base 3. So what I will do is I will convert this to a base e. Right, so this is actually a ln 5x over ln 3, right? So that's how we convert bases. So this is the same as 1 over ln 3 times ln 5x. 1 over ln 3 is just a constant, right? So it's quite simple to treat a constant. So dy dx would be the constant multiplied by the derivative of ln 5x, right? Which is 5 over 5x. Okay, and after simplifying, we should get 1 over x. Okay, so that's how we differentiate that. Okay, so let's look at a few more examples, right? So for this, we have to use product rule, right? So I can let this be u and I can let this be v. Okay, so dy dx would be u times dv dx, which is 1 over x, plus v times du dx, which is just 1. So this is actually 1 plus ln x. Okay, so let's look at example 25. Again, we can use product rule. We can let this be u and this be v. Okay, so dy dx would be u times dv plus v times du, right? So differentiate of sine x is cosine x. Okay, so this is just 1 over x sine x plus cosine x times ln x. Okay, so for example 26, we can use quotient rule. Right, so this is u and this is v. So dy dx is equals to v times du dx, which is cosine x, minus u times dv dx, which is 1 over x, right? Over v squared. Right? So this is the square of ln x. Okay, so you can just leave your answer like that. It's really nothing much to simplify. Okay, and what about example 27? Right, so example 27, we can actually use the general rule. Right, so the fx is actually sine x. So dy dx is just the derivative of sine x, which is cosine x, over sine x. Okay, so you should get cotangent x. Okay, and finally, let's look at how to differentiate exponential functions. Okay, so this is the standard one, right? So when you differentiate ex, e to the power of x, you will get e to the power of x again. Okay, but generally, if you're asked to differentiate e to the power of fx, it is basically f prime x times e to the power of fx, right? So it just happens that the fx here is x, and you differentiate x as 1, right? So it makes no difference. Okay, so let's look at example 29. Okay, so the fx here is x squared plus 2x, right? So if I differentiate x squared plus 2x, I will get 2x plus 2, followed by e to the power of fx, which is e to the power of x squared plus 2x. Okay, so let's look at example 30. The fx here is sine x. So if I differentiate, right, I have to differentiate sine x, which is cosine x, multiplied by e to the power of sine x. Okay, so let's look at example 31. So of course I can apply the same rule here. Okay. So dy dx, this will be equals to differentiate of ln x, which is 1 over x, times e to the power of ln x. Okay. And this is actually equals to 1 over x times x. And that is equals to 1. Okay. So this is actually a big detour, right? So if you notice, e to the power of ln x is actually x, right? So this is as simple as y equals to x. So if you differentiate x with respect to x, it's just 1. So if you have noticed this earlier, you would have, saved quite a bit of time. Okay, so in general, e to the power of ln fx is equals to fx, right? So that's because the exponential e and fx and ln x, they're actually inverse functions of one another. Okay, so let's look at a few more examples. Right, so this one we can apply product rule. Right, this one can be a u and this one can be a v. So dy dx would be u times dv dx plus v times du dx. Du dx would be cosine x. Okay, so you could have factorized out e to the power of x if you wanted to. Okay, so for example 33, we have to use quotient rule. This is u and this is v. Right, so dy dx would be v times du dx minus u times dv dx over v squared. Okay, so you can factorize out e to the power of x, and this will be x minus 1 over x squared. Okay, finally, let's look at example 34. So again, this is not e anymore, right? So this is a constant. E is 2.7 something, right? It's not 2. So how do we differentiate something like that? Okay, so what I will do is I will introduce ln to both sides of the equation, right? So ln y will be ln 2 to the power of x. Okay, ln y is actually x times ln 2, right? So using the rules of logarithm, I can bring down the power. Okay, so I'm going to express y again in terms of x. So y is equals to e to the power of x ln 2. So ln 2 is a constant, right? So this is actually similar to saying that, okay, this is e to the power of ax, right? And when you differentiate that, right, a being a constant, this is just a times e to the power of ax, right? So the same applies. So dy dx would be ln 2 times e to the power of x ln 2. Okay, so we could actually simplify this further, right? E to the power of x ln 2 is actually ln 2 to the power of x, right? We can bring the x to become the power of the 2, right? So by the rules of logarithm. And if you recall, e to the power of ln fx is just fx, right? So this is actually ln 2 times 2 to the power of x. Okay, so in this case, this is the fx. Okay, so yep, we have finished the short course for differentiation. Hope you find this helpful. I'll see you in the next video.